everyone. Welcome to day 3 of the workshop. We're going to switch topics a little bit today. We've been talking about privacy and civic participation. Today, we will move more into sort of trustworthy algorithm design and machine learning. We'll talk about fairness, interpretability, and as well as some applications into healthcare today and then going into tomorrow. So it's my pleasure to introduce our first speaker today. Juba Ziani is an assistant professor at Georgia Tech, and he has done a variety of different things in the space of ethical computing. So thank you.
Yeah, thanks a lot for having me. Pretty excited to be here today. So today I'm going to tell you about work on pipeline interventions. It's joint work with some of my collaborators at Penn. So Ishwar Ram Arunachal Iswaran, Sampath Kannan, and Aaron Roth. So basically today I'm going to tell you about fairness. I think a lot of you guys who are in the room right now are here because you care about fairness. So, nothing too surprising here. But the kind of point that I want to try to make to begin this talk is that, yeah, okay, we should actually care about fairness in practice, because nowadays we're using algorithms and machine learning to make a lot of really important, possibly life-altering decisions about people. And we know those decisions can often be made in a very unfair manner. An example of this, for example, is still that there are still today really persistent disparities when it comes to access to mortgages and loans across different populations. And this is really a setting where machine learning actually gets to play a role, because, well, that your likeliness to actually get a loan is going to depend on your credit score. So it's kind of like a black box, hard to understand machine learning algorithm. Banks, when they also make decisions, they have their own algorithm, they have their own decision trees they're going to be using to decide whether someone is going to get a loan or not. And that can actually, algorithms are applied in arguably even higher stakes settings. One of them is kind of policing, predicting policing and the justice system. And so once again, here we know there are really big disparities across different populations. And once again, this is a setting in which people actually kind of use algorithms to kind of make decisions. One thing that I'm sure you've heard about is there are algorithms that kind of try to predict where crime is actually going to occur, where crime is going to happen, and use that to kind of allocate police resources, this kind of machine learning based algorithms. There's even algorithms now that are used to inform whether someone should get a bail or not. And those algorithms have been kind of shown to be really unfair. Okay, so here, kind of what I want to point out is generally the traditional view of what's going on is, okay, we're going to run a machine learning algorithm, we're going to run a classifier. Here I just brought down a linear classifier to make it pretty simple. And we can say, okay, well, let's look at how this classifier is going to treat different populations. And you can say, in this example, it seems at a high level that if you look at what the classifier is doing for group A, imagining the green people are people that are classified positively, and what it's doing for group B, there is something a bit sketchy going on, and we have to worry about this. And it's kind of how people traditionally think about fairness and algorithmic fairness. But today I kind of want to move away from this a bit. So generally the question is how do I make this one classifier fair? But as you saw, the title of my talk is about pipelines. And so I'm going to try to convince you that you shouldn't care about a single decision and a single algorithm, but you should care about a pipeline of many composed decisions. In real life, it's almost never going to be about a single decision that you're going to be making about an individual. Rather, you're going to make several decisions about someone, throughout their life, for example, and those decisions, they're going to affect each other and they're going to compose with each other. If I here, kind of the example that I have is an example in which I'm looking, for the sake, of this talk, I'll look at kind of an education pipeline. I'm going to say, well, what's going on here is that, what preschool you're going to go to is going to affect kind of your access to what kind of elementary schools, middle school, high schools you can get to. That's going to affect your college opportunities. That's going to affect your job opportunities. So you can't just think about what's going on one level of this pipeline. You have to think about the entire thing. The point is that inequality of access to opportunities in those kind of pipelines can arise at several of those points, and they're going to compose with each other. Like if I have like disparities in my opportunities right here. Okay, I don't know how to use a clicker, I guess. If I have disparities in like, opportunities right here, well, this is going to kind of like also affect your future access to opportunities. If you have like disparities in access to opportunities right here, that might have been caused because of like past disparities and inequalities in access to opportunities in the past. And in real life, in the education pipeline, we know like those disparities can really arise at the very, very early level. It's really hard to get into a good preschool in the US, for example. That's kind of like what I want to model today. And then, once you have a pipeline like this, the question is like, where are you going to intervene? And, once again, if you look at the education pipeline, I think it should not be too hard to convince you that if you're trying to intervene only at the college admission level to try to fix college admissions, that's probably not going to work. It's probably not going to be enough. So you need to think about the whole thing. So it's maybe worth intervening before in this pipeline. Now, if you're saying I'm going to be intervening in this pipeline at several possible stages of this pipeline, you now have to reason about, wait, what are those interventions going to do? How are they going to compose with each other? And how do you optimally kind of like design interventions at like several levels of this pipeline to kind of like improve outcomes and to reduce disparities over groups, whatever that means. And I'll get to whatever that means in a bit, because there's possibly different ways you could define how you want to improve and reduce those disparities. Before I get into the technical meat of the talk, I just want to point out that there is some other really interesting work in the space of kind of like composed decisions in fairness, especially those 3 works. I'm sure there are others that I probably forgot about, but I also know that these people are here at Simons this week. So I just want to make sure that I'm highlighting them. I saw Christina run at some point, and I know that Kevin is right here. So yeah. Anyway, so now let me start talking about the math and talking about how we're modeling this. Before you tell me my model is wrong, I know my model is wrong. It's a very stylized model, okay? It's a very high-level stylized model so that we can try to think about those disparities. There's definitely a lot of ways you can improve it. So just remember, this is abstract. And I'm not trying to claim that I've solved real life. That's not true, okay? But yeah, and so kind of here are the points. What we're trying, the way we're going to model this is we're going to have, well, this pipeline that's going to be comprised of several layers. So we're going to have this kind of graphical model. And let me actually go through this model right now. But the first thing is we're going to say we're going to have a first starting layer right here. It's going to have a bunch of different nodes. And we're basically going to say those are kind of the starting populations. This is the kind of population you're going to start, your life in. This could be, yeah, okay, so different nodes here are going to correspond to different starting populations. It could be different socioeconomic statuses, for example. And then, you're going to go from the starting layer and you're going to go through the layers one by one. So what's going to happen here is each of those layers, they're going to correspond to possibly a different stage of life. And each node in that layer is going to correspond to an outcome of this stage of life. You can imagine, I don't know, maybe layer K-1 is your kind of education after high school. And it could be that, I don't know, one node is you go to college. One node could be that you decide to get a job right after finishing high school, for example. And finally, what's going to happen is at the end, you're going to end up in this final layer. This final layer is going to have a reward pretty much, which is going to be a measure of how good the outcome you end up in is. So the bigger R is going to be, the better the outcome. I'm going to say here. So now I kind of told you about the layers. I haven't told you how we're going to move across different layers. But here, for the sake of this model, for the sake of simplicity, we're going to assume that we kind of have stochastic transitions. So there is some probability that if you start in this node, you're going to end up in this node on the first layer, and it's going to be given by kind of a transition matrix here, M1. So a transition matrix M1 is going to basically tell you what is the probability of going from a node on layer 1 to a node on layer 2. And this is kind of where you can start modeling disparities between different groups, because you can say, oh, maybe this one is people of a really high socioeconomic status, and they have a lot of high probability paths that go to kind of the best nodes in the graph. versus those people that have like a really low economic, like socioeconomic status, they have access to almost no opportunities. So most of their transitions are actually going to go towards like the lower quality outcomes in the graph, for example. So it's kind of like how we're thinking about the disparities in this model. So now we have a pipeline like this, and we want to intervene on this pipeline. What do we mean by intervening on this pipeline? Once again, this is going to be pretty, this is going to be kind of like pretty stylized, but we're going to look at a setting in which we have like a centralized designer that can decide how and where to intervene on this pipeline, possibly at several stages at the same time. And like the intervention is they're going to be able to change the transition matrix between any two layers they want. That's going to come at a cost, though. You can't do that for free. The more you're going to change the transition matrix, the more costly it's going to be for you. And so we're going to have this cost here, which is basically what I'm calling C of MT0 to MT. Here is the cost of going from like an initial transition matrix MT0 between layer, let's say T and T+1, to going to a new transition matrix M of T. Just for the sake of optimization, I'm going to assume this cost function is going to be convex, because if it's not convex, we can't really say anything. And basically, we're going to say that we have a budget constraint across the whole pipeline. So you have some budget that you can allocate across the pipeline. You need to decide how you're going to split up this budget across different stages of your pipeline and how you're going to change the transition at each stage. So that's kind of like the high level idea here. Yeah.
I was wondering if you make any assumptions about how the costs change through the pipeline. So, is it easier to make interventions early on in the pipeline versus later on?
So what I'm going to be doing in most of this talk is going to not make an assumption and just like be purely algorithmic and tell you how can I solve this pipeline. Later on, I'll talk a bit about kind of like what happens in like a very special case of pipeline, and which is once again stylized and unrealistic. I'm going to tell you about what happens when the cost at every layer is the same, which is not really what happens in practice. But let me get back to this a bit later in the talk. Yeah. Okay, so I told you about the model. Kind of like our second contribution here is to actually have dynamic programming algorithms to find approximately optimal solutions in this problem. And so basically, what we're trying to do here, remember, is like we need to figure out how we are going to split this total budget across different layers. And then each layer, we need to figure out how we're going to use this budget to change the transition matrix. And so, yeah, we're trying to do this optimally. I haven't told you what optimal means here. I haven't told you yet what optimal means here because we have two different definitions of optimality that are going to actually have different properties here. And the first one is say, okay, we want to try to maximize the social welfare of the population. So you look at a sum, like a weighted sum by population size of the utilities that people get when they go through this pipeline. And you say, I'm trying to maximize this total like utility. And like social welfare is like a pretty common objective that's used a lot in a lot of different fields. But I just want to point out that what this is going to do is going to tell you what's the best thing you can do at the level of the whole population. It's not going to say anything about any subpopulation. It's not going to tell you anything about how this welfare is going to be split across different populations. So you might just end up in a situation in which you just allocate all of your resources to the very large population and you completely ignore the subpopulation that you should actually care about. Which is why we also have objective number 2, which is the maximin welfare. And now we're trying to maximize the welfare of the worst of population. So just saying, I'm going to pick those transition matrices here so that if you start in the population I, well, basically your utility can be too low. So I'm trying to maximize these quantities. I'm trying to make sure that like for every I, for every starting population, the utility you're going to get in this population is not going to be too low. Yeah.
I guess when you're changing the transition matrix, like are there constraints? When you're changing the transition matrix, are there constraints? Because I would imagine that like, okay, at least some people would think that some people get better off at the cost of other people getting better off. So like if you're looking at the high socioeconomic status, there's only so many people can be doctors, blah, blah, blah.
So there could be constraints. I'm not going to get into too much details about this because they're kind of like all abstracted away in the cost function. But like towards the end of the talk, I'll get back like a bit about this point and like what kind of like, yeah, what can happen there and like how, like what kind of like settings this setup can model. So I'll tell you a bit more about this. Yeah. Okay. So now that I told you what the model is, it's time for math. This is going to be the rest of the talk, by the way. Like everyone else had like really amazing talks and like a lot of kind of like super cool motivation, really nice slides and everything. You're going to be staring at pictures like this for the rest of the talk. So I apologize in advance. But yeah, let me try to start with a very simple setting in which I only have 2 layers. So it's like it's not a pipeline anymore. It's just like a one-time decision. How do I want to solve this problem? Okay, well, imagine, so this is like my starting population. So this is my end nodes. So here I have kind of like a distribution over like, what's the probability you start with like a high socioeconomic status. That would be kind of like D1 here. You start with like a lower socioeconomic status. So this is just the probability that you're going to start in each of those nodes. And then, you go through the transition matrix and then you get those payoffs. If you end up like at node number 1, you get R1 and, it keeps going this way. If you think about it, that's actually a really easy problem because what am I trying to do here? What I'm trying to do, and like here I'm going to talk about the social welfare, not the minimax objective, but the minimax objective is actually not going to look very different in terms of optimization. But just for the social welfare, well, my social welfare is just kind of like a linear function of the M1 edges here. It's just kind of like R times M1 times like the starting distribution. This is how much social welfare people are going to get. And now I have a convex budget constraint, which is that I just want to use my cost here to go from M10 to M1. I want this cost to be less than my total budget. So nothing crazy. It's a linear program with a convex constraint and some convex optimization. You can solve this. Not hard so far. Yeah, well.
Oh, sorry. No, I just didn't get the joke. Can you go back one slide?
Well, because we've been talking about differential privacy for the past 2 days. But yeah, that was the joke. Anyway, okay, so now I was just like telling you what happens when you have 1 layer. Well, when you have many layers, we're going to go backwards and we're going to start here and then we're going to solve this layer and then we're going to solve this layer. I'm going to do some dynamic programming backwards. Sounds simple enough at a high level, but there's a worry here because, okay, so imagine I want to start at the last layer. So I want to kind of like find the best possible MK right here, given that, and I'm going to skip quickly on this, but like imagine I already know how much budget I'm going to allocate to this layer. I'm going to call that DFK. Well, the problem that I want to solve is kind of like the same as before. It seems simple. It's a simple convex optimization problem, assuming you know decay, except that you don't know decay because decay depends on the decisions that you're going to make on the rest of the pipeline that you haven't made yet. So it's going to depend on the early transitions. And since we're solving from the end, we haven't solved for this yet. So it's kind of like why things get a bit more complicated. But so, since we don't know what the D of K is going to be here, what we can do is we can try to guess it. So we're going to try to guess every possible D of K. We'll take an epsilon net up here of like the possible probability distribution over those nodes. Sadly, when you take this epsilon net, well, if you want an epsilon net and you have W nodes on each layer, well, the size of the net is going to be 1 over epsilon to the power of W. So if W is not constant, it's going to be really hard to do anything. I'll get back to this in a bit. That's actually kind of like unavoidable. And then I'm going to try every single D of K on the net. I'm going to solve the program for every possible D of K on the epsilon net. Then I'll go backwards. And so I'll go to the layer right before. I'll do the same thing. And I'll say, OK, well, here I'm guessing all the possible DFTs as before. Here, I need to figure out what the R of T is going to be, what the reward is going to be. But there's going to be 1 reward for each distribution on the epsilon net that I did in the previous layer. So I'm just going to have to go through all of them, but there's not going to be that many of them. There's just going to be, assuming that W is constant, I'm just going to have to deal with like, 1 over epsilon to the power of W things here and like 1 over epsilon to the power of W things here. So it's not going to be bad. If the W is constant, you can do this. And here, so yeah, so you're just going to use the solution to the previous steps at this point. Finally, quick thing is, so far, I'm assuming that I know what budget D of T I'm using at each time step. It's actually not too hard to figure out what that budget is going to be, you can also use like a dynamic programming approach for the budget. You just discretize the budget. It's easy to discretize. It's just a one-dimensional scalar thing. So you just discretize the budget, and every time step, I mean, every like level of the pipeline, you guess the possible budget you're going to be using there. And you try out kind of like all of them. But there's only a small number that you have to try out, so it's fine. Yeah.
Hey, is there a reason we can't do this second DP approach first, where we like start at ground one and discretize a budget and say like solve this for every big B over epsilon?
You can start at the beginning. That doesn't change anything. You could have
don't we
approach,
know the distribution for every B, like what B over epsilon then?
Well, if you start at the beginning, if you start from the first layer, you don't know the distribution of rewards, so you have to guess that. No matter which way you go, you're going to have to guess one side. But it's going to be the same approach if you start from the beginning. All right, but anyway, just like to tell you what the algorithm, I mean, I told you what the algorithm does, but like in the end, the kind of guarantees that we're going to get is it's going to be approximately optimal because we're just losing like an epsilon roughly in terms of social welfare each layer. So we're just going to lose k epsilon total. So we're going to get like a k epsilon approximation. If we have k transitions, if you're assuming that w is constant, you'll just need to kind of like solve like 1 over epsilon w problems at each layer. And you're only going to have to do this k times. So that will be efficient. And actually, so it's like, so for once again, like for w constant, but k could be very large. It's like linear in k. So you could actually technically think about like a very long pipeline. You just need a pipeline in which at each level, you're going to have like a kind of like coarse grouping of outcomes so that your w is not too big. And finally, for the maximin objective, you can actually do exactly the same approach. It's just a bit more complicated because now you actually have to keep track, instead of keeping track of all the possible like distributions d of t at a layer, you need to keep track of all like d of ti, one calling d of ti, which is kind of like the specific distribution for population I. So it's just going to give you kind of like, it's going to be the same approach. It's just going to give you like a quadratic blow up in w, which is a constant here anyway. So it's not really going to change that much. Okay, so now I told you that there is this w, which is kind of like pesky and annoying here, because we have this dependency in 1 over epsilon to the power of w. This is actually just unavoidable. The problem is hard for non-constant w. And that can be seen via a reduction to vertex cover in this case. I'm sure most of you guys know what vertex cover is, but just to give you like a quick example, like, okay, what do I want to do in vertex cover? I want to pick the minimum amount of vertices that are going to cover this, like a given graph. Are going to cover all of the edges in the graph. So in this case, those two vertices give you a vertex cover because the red one is going to cover those 2 edges in red, and the green one is going to cover those like 3 edges in green. And the reason we want to use vertex cover is because, well, I'll show you the reduction in a second, but vertex cover is a hard problem. It's not just hard to exactly optimize. It's hard to approximately solve. Vertex cover is not just NP complete. It cannot be approximated to a constant factor. And we'll use this to show that in our problem, we also cannot approximate our solution to a constant factor. And this is kind of like what the reduction is going to look like. It looks a bit scary, but let me just go through this. It's actually not that complicated. This is actually, if you look at it, it's a very simple pipeline. So don't worry about those things. They're just here to make sure that the like transition matrices are going to kind of like sum up to 1 properly and everything. It's just like dummy nuts. You don't need to care about this. What you really want to care about is what's going on here. And what I'm saying is like, I'll take every edge UV in my original graph, and on the graph on which I'm trying to solve my vertex cover problem. And I'll say for every edge UV in my original graph on which I'm trying to solve vertex cover, I'll kind of like assign a starting population. I'll assign a starting population, and I'll assign 2 paths to the end, and 2 paths through the pipeline. And there's going to be 1 path that corresponds to U, and there's going to be 1 path that corresponds to V. Does that make sense so far? What I'm going to tell you is, okay, so if I want to do, and here like the hardness result is like for the minimax fairness case, just to clarify this. But if I actually want to get a good minimax fairness guarantee, I need to make sure that like from, I get to a good outcome of 1, rather than 0 here for every starting population. But I want to do this because I have a limited budget. I want to do this using as few paths as possible. That's kind of like where the vertex cover thing is coming from now. So I'm saying here I could kind of like use this path, and I could spend budget on this path, and this is going to give me a good outcome here because I'll get to 1 starting from UV here. But that might not be the best solution, because if I have a situation like this in which here it's UV and here it's VW, well, they're actually going to share that V path right here. And I should be using this V path instead of using a U path and a W path. That's going to use more budget. It's going to be less efficient. So I kind of like want to use like the minimum number of paths. But now what's going on is when I pick a path, picking a path is the same as picking a vertex in the original graph. I'm telling you, if I'm picking this, I'm actually putting V in my vertex cover set. So if I minimize the number of paths I'm using, well, I'm using as few vertices as possible in the original problem. And so this is how this reduces to vertex cover. And so, yeah, and so this is why we kind of like have this hardness result that we're not going to be able to approximate to a constant factor in this case. Finally, kind of like the last thing that I want to mention is that we also kind of like have results on kind of like the price of fairness, because we're trying to understand, the gap there's going to be between those two different objectives. What happens when you're trying to optimize social welfare versus when you're trying to optimize the minimum utility of across the different populations. And this is where I was telling you, okay, this is another kind of like unrealistic case, because here I'm going to assume that there is a linear cost of 1 by, like, if you want to change the transition by 1, and it's going to be true everywhere in the pipeline. In practice, you kind of like also want to think about pipelines where, like the closest you are to the end, the harder it's going to correct for past disparities, and like it's going to become more and more costly. And just there, I just want to point out that we actually have kind of like tight bounds on what this price of fairness is going to be. And there's like 3 different cases there that are for kind of like very, very small b. This one is not that interesting. It's a bit of a corner case. I'm not going to cover this really. There is another case which is for very large b. It's trivial, if you think about it for a second. So I'm kind of like going to focus on like this intermediate case, which is kind of like interesting because it's showing some interesting structure and like how you can actually intervene on such pipelines. And so let me look at what's going on there, like give you some intuition of why we have this dependency on like W over B. So okay, so imagine again, I kind of like have this whole pipeline. And remember that I'm like in the special case here where intervening here has the same cost as intervening here, right? One thing I can try to do is actually just forget about all of this and intervene at the end. If I intervene in the beginning and I change my transition at the beginning, there's still going to be a lot of transitions left that are going to push me back towards possibly bad outcomes. It might not help me that much. If I intervene at the end on the last layer here, you would be like, well, I can actually have a lot of control on like what reward people are going to end up in. Okay, so really what I want to do is I want to push people as much as possible towards this reward. And if I kind of like want to here guarantee that every population is going to kind of like get like a reasonable social welfare, I can just say that like for every node on this layer, I'm going to increase the transition by B over W. If I do this, I'm guaranteeing that everyone is going to show up at like one of those nodes anyway here. So at this point, with probability B over, you're going to increase the probability of everyone going to the highest reward by B over W at least. And so, you'll get a mean max welfare that's going to be at least B over W times R1, the highest reward. If you want to compare this to the social welfare, well, the best social welfare you could get is like if somehow you manage to get everyone to R1, that's good. And you would get like a social welfare of R1. And so that's why you have a price of fairness that's going to be at most B over W in this case. And it's actually kind of like tight here. We're not going to get into like yeah.
Assuming that the highest reward is what everyone wants.
Yeah, I'll get to this in a second. I'm assuming that everyone wants the same highest reward, which is another assumption of the model.
Right, like if I was thinking about education system, people would have different preferences to
right. Yeah, I completely agree. Yeah, it's just like that's why I'm saying this is a very stylized model. It's like a
But
first
do you
gut.
have thoughts of extending it to that case?
Yeah, no, I've been like, I mean, I haven't made any progress on this so far because I got busy. But this is definitely one of the directions that I've been interested in like working on in this case. I just don't have good insights for you right now on how to solve this, but yeah. Okay, so anyway, actually, since what I'm getting to here, I kind of like want to have the last couple slides once again saying that this is a stylized model. It's not completely realistic. One thing that you may complain about, and so would be a very valid complaint, is, oh, well, if I look at this graph, well, different populations are going to face, if population one, population two get to this node, then they're going to face the same transitions. And say that's not what happens in practice. If you come from different subpopulations, you can get to the same point in life and still face different opportunities. So what happens there? And one thing that I want to point out is we can actually model this in our setting. You can duplicate this pipeline. You can duplicate the nodes so that instead of having just like one node for each outcome in a layer, you have one node for each outcome and starting population. And the way you can link those together and link those interventions together is by kind of like playing with the cost function and having the cost function such that, if you modify your transition matrix for one population, it becomes cheaper to modify it for another population. So you kind of like the cost function is set up so that it's going to naturally make you kind of like change the transition for several populations at the same time. So this is one way you can model this. It's just going to be kind of like giving us a quadratic blow up in our algorithms because now you have a pipeline that's going to be like bigger. Before it was like only W nodes, now it's going to be W squared because it's going to be W outcomes times W starting populations. Okay, but this is something we can kind of like handle here. This is one thing, and there's a million other things we can think about to try to extend this model and improve this model. One thing is like, it's weird to assume that transitions are going to be stochastic because people do make decisions in real life and people are going to be trying to like go towards specific nodes. So it would be interesting to model what happens when you actually have those kind of like strategic elements there. We don't have any feedback loops. It's a really acyclic model here. So you go from beginning to the end. And once you reach the end, that's it. The problem is over. We're not taking into account how this is going to affect kind of like the next population, for example. This is another thing you could model. So this one's for you. We have a very simplified model in which everyone wants the same rewards, but not everyone in life wants the same outcomes. Not everyone gets the same utility for getting to the same node and getting the same outcome. Another thing is we're assuming there is one centralized designer who can intervene on the whole pipeline, but in real life, each of those different levels of pipeline, people are going to be doing their own thing. They're not going to have like one centralized person who's actually changing the transitions of that whole pipeline. Another interesting direction, I think, would be if someone has real data and wants to kind of like try to see if you can model this pipeline using real data, that'd be really interesting. Many others. But basically, that's kind of like all I wanted to mention today. So like, once again, yeah, thanks for coming to my talk.
Hi, Juba.
Hey.
Hi, Juba. Is this on?
Yeah, it is on.
Hi, Juba. I really enjoyed the talk. If it's okay, I have a two-part question.
Okay.
One, when you're doing the model, did you think about allowing people to get utility from intermediate layers? So rather than the ultimate layer. And my second question is, capacity constraints on nodes, or like maybe like the utility from one node goes down as more people enter it, or possibly increases.
Okay, let me talk about those two things. Number one, I believe is easy because you can just, if you have intermediate rewards at each layer, you can just kind of like, go back quite a few slides, give me a sec. Like when you're solving this kind of problem here, you can slightly modify the objective to take into account that you actually have like an additional reward there.
It's like having a bunch of last layers.
They're just like, you have like, you have your R1 plus some intermediate reward. It's not going to change the problem by much. You're still going to be able to solve this. So that's fine. Question number two, I actually spent some time thinking about capacity constraints in this problem at some point, and like, kind of like settings in which the difficulty to like go to a specific node, and the next layer is also going to depend on number of people that end up going there, and like that kind of transition. And it was very hard to think about and make zero progress in this. But you have like a good idea to try to solve this, that would be a very interesting future direction. I agree.
Yeah, just a comment there. Seems like a sort of congestion game if you take capacities into account. So work on.
Right. So when I'm talking here about kind of like those strategic elements and everything, I actually at some point was thinking about like trying to model this as a congestion game. But it's really hard to think about because you're thinking about a congestion game and you're thinking about how is the equilibrium of the game going to change when you're changing the capacities or transitions or costs in the game. And I was only able to make progress on this in like very special cases that are kind of like trivial and not that interesting. So yeah.
Yeah, really nice talk. So it's kind of a comment, but since you motivated this talk using like algorithmic fairness and saying how algorithms can be unfair, so are you assuming anywhere in the system that there's algorithms involved, or I feel like everything here doesn't really have to do with algorithms.
Right. So like the point is like the transition matrices are kind of like a way to really abstract away, once again, so this is very stylized, like we're really abstracting away from like the process by which people end up from like, you know, like node 1 and like layer 1 to node 1 and layer 2. So you can kind of like try to think about those transitions as transitions that are induced by real decision-making processes by real algorithms, but like we're not explicitly modeling this here.
Right, but this doesn't necessarily have to be algorithms, the transition.
It doesn't have to be algorithms. It could be kind of like just decisions and everything. But this, yeah, also depends on your definition of algorithm, because I would say that, you know, something like, you know, you want to get into college and you have to take SAT or the GRE, those are technically kind of like algorithms that map your like inputs to a score. That is supposed to predict how qualified you are for the job. Sorry, for the university. Yeah.
Nice. So, so I probably should have asked this a lot earlier, but can you compare this model to just a constrained Markov decision process, finite horizon, because it looks very similar to me.
It is absolutely a Markov decision process. It's just one that happens to be very structured, so we can actually say something about it just because you have like this kind of like really nice layered structure, but it is a Markov decision process.
Yeah, but then I'm wondering where exactly the hardness comes from, right? Because there you usually have like polynomial time algorithms, like dynamic programming is like super nice, but where is that hardness coming from?
So first, I should admit that I'm not an expert in results in Markov decision processes, but I think like if you look at them in a whole like full generality, they can still be hard to solve, right? Here, just I think the difficulty is really just coming from the fact that what's happening is the number of possibilities you get each time is kind of like blowing up exponentially, and like the size of those layers, and it's like making things, you know, worse every time, just intuitively at a very high level.
Right. Yeah, and I guess
Like,
it also comes from the fact that you're using these very general convex coasts as well.
We're also using very general convex costs in that sense. So it's kind of like, yeah, I think if you have like simpler costs, it might actually be like easier to kind of like solve this problem.
For example, if the coasts would be decomposable like column-wise for the matrices.
Well, I mean, there may be a class of costs for which this is simple, but this, where is this? This is using linear costs.
Oh, I see.
Very simple costs. So there may be some class of costs that have like a nice structure that just composes perfectly and everything works out fine. But even very simple costs like linear costs seem to be hard. So yeah.
I see. Very cool. Thank you.
Juba, I was wondering, you kind of motivated your talk by saying, well, we have these pipelines where like perhaps we want to think about intervening at the beginning rather than just at one particular step. But then in your very simple model, right, the stylized one where you're looking at price of fairness, you were like, let's ignore all the earlier ones and just look at the last layer. So can you say a little bit about like if we wanted a very simple stylized version of your already stylized model that captures that effect, like what would you include that's not kind of in that?
Right. Yeah. And so no, that's a really good question. Like this thing is just really for the sake of example. And Like the only reason you can do this here is because the costs here are like the same as the cost at the beginning. But you would imagine that in real life, if like the costs here are like much cheaper and the costs here are going to kind of like be much higher, then you're going to try to balance out. You'll like the layers at the end because you have more control over the transitions, but you'll spend more, like less on them because it's too costly to do so, and you're going to start splitting more. One way you can actually see this is if you look at like a very super simple pipeline, which is just a bunch of paths. And like this person goes this way, and this person goes this way, and this person goes this way. And you say, okay, it's kind of like not costly at the beginning, it's very costly at the end. On this path, if you want to maximize kind of like the probability of like transitioning to kind of like say R1, I mean, there. So, you know, it would be kind of like a very simple binary case, like you're either 1 or 0, and like you're trying to increase your probability to go to 1. You want to increase every level of this path because kind of like by a convexity argument, it's like better to split your budget across the path rather than like using all the budget in one layer. But you're going to do this in a way that kind of like also depends on how much cost there is. So you're going to put less weights on this last thing at the end because it's becoming like way more costly. So like intuitively, that's what's going on.
Okay, let's take further questions offline. Thank you very much.
Well, thanks for having me.